Welcome back to another episode of Dennis yapping while trying too hard to build a 3D printer. In this episode, we're going to be finishing up all the external hardware details in this printer. Stay tuned for more RGB lighting than I know what to do with, more hexagons in random places, more cameras in weird places, and maybe a few other surprises later on. Before we get started, a quick word from this video's sponsor, which is me. Everything in this video series is now open source, with documentation on GitHub and CAD files on printables in case anyone wants to reproduce anything from these videos. If you've been waiting for the CNC bed frame mod, it's gotten a bunch of quality of life improvements since the last time you saw it. First, the holes are actually in the right place this time in the CAD, so you don't need to do any re-drilling like I did. Parts of the bed have also been thickened so that you can pre-thread the holes to simplify the installation process. Also, there's now a proper mount for the Wagger connectors, so you don't need to glue them in anymore. On the electronics side, there's a new STM32 based bedboard which sits under the bed. The old board that I showed in a previous video was based on an AT Tiny chip which required extra calibration to get good temperature readings. The old board also only supported one-wire serial, while the new STM32 based board supports either one-wire serial as before or a standard two-wire serial that is compatible with Clipper. Making these as one-offs can be a bit expensive, so I've partnered with Vitali 3D to bulk manufacture a bunch of these CNC bed mods to help bring down the cost. You can buy them now on his website in either black or silver color. For now it's just the bed frame, as we're still working out the details for directly selling the other parts. Links to all this stuff are in the video description. Anyway, so first we're going to be adding one of these cameras to my printer so that we can do remote monitoring. The specific camera I got is the 3DO enclosure camera, which comes with a camera sensor, optionally a flat expansion cable, a logic board, and a USB cable to connect it back to a Raspberry Pi. Most of the existing mounts I've found look like this and mount the camera all the way in the back, which makes the wiring a lot easier, but it's kind of weird to be looking at prints from the back side. So instead I designed this camera mount which mounts to the front of the printer. Basically you first insert the flat flex extension cable into this hole, then you can snap in the camera module. The 3D printed piece then attaches to the front of the printer using two of the pre-inserted nuts we added way back in part 1 of this video series. Here's what it looks like once it's fully on. And here's what the view looks like when you plug it into your computer. The sensor is natively a 4:3 aspect ratio, so that's why there are black bars in this frame. Also, if you're smarter than me, then you've probably noticed by now that this camera mount cuts out a 15mm square from the corner of the build area if you mount the camera in the highest position. So I wouldn't generally recommend people use this mount. Before we do the cable routing for the camera, we're going to first install some lights. If you look a little further back in the printer, I added these panels back in part 1 of this video series to provide some extra insulation, and they also have these screw holes pre-drilled for mounting lights. Or we're going to use them to install these RGBW light strips from Provoc 3D. I bought these a while ago, but I've heard that Provoc 3D has been having some issues with filling orders recently. This mod is compatible with other matchstick LED strips, but just be aware that the RGB and white ones have different screw spacings. Anyway, I'm going to be crimping some custom cables for these, which for now have one side uncrimped. Then I printed this matchstick diffusers mod that I found on the internet to hold the strips. To mount the strips to the walls, I made these custom L-shaped clips with heat set inserts on both sides. The special thing about these is that they have this little cutout on one side, which will let us route the flat flex camera cable behind the light strips to make it a little bit more discreet. Anyway, we can screw these into the LED strips and close them up with the diffuser. The cables go through holes in the mid panel behind the bed, which we drilled out back in part 1 of this video series. And now we can finish screwing everything together and do the same on both sides. Finally, we can route the camera flat flex cable through the LED strip clips and through the mid panel hole. If you try doing this yourself, it may help to route the camera cable before attaching the LED strip fully. And on the other side of the mid panel, the camera cable attaches to the camera logic board, which I'm going to wrap with electrical tape to make sure nothing shorts out. Before we finish the wiring, there's still one more sensor we need to add. If you watch my previous videos, you'll know by now that I'm an expert in not following the directions in the Voron manual. Well, I'm forcing myself to finish everything in the manual in this video. The first thing I missed is the filament sensor that detects if filament is inserted into the body and also functions as the inlet for filament into the machine. There's nothing super interesting about this process, but I need to do a little bit of backtracking to remove one of the legs. Then, following the Voron 0 instruction manual, I inserted the bearing and screw into the hole in the leg. I hooked up a multimeter in continuity mode to the switch and made sure that when I insert filament the switch triggers. If you read the instruction manual, it suggests adding tape to the bearing if the sensor doesn't work, though in my case I didn't need to do this. Then I can finally reattach the leg to the printer, and now we can add another filament tube to make a full filament path from the leg, through the presence sensor, through the filament movement sensor, and then into the tool head. So now we can deal with all the wires in the back of the printer again. First, I need to do a bit of unplugging to make it easier to work here. The filament sensor in the leg attaches to this final connector on my main board. Then, since all my existing boards already have all the connectors used up, I'm adding another board near the top of the printer using another 3D printed adapter. the LED strips attached to the left and right connectors on this board, and the magnetic filament monitor we added in the last video also attaches to this board. Then I've got to finish running all the USB wires and reassemble everything. If you've been keeping track, this printer now has around 8 different PCBs installed and desperately needs some consolidation. As a quick teaser, for another project that you'll see in a few weeks, I've been learning how to make custom compute module carrier boards, so expect one from my Voron in the future. So now we can start sealing up the printer with the exterior panels. If you are using this video as a guide, now is a good time to make sure you have 5 pre-installed M3 nuts in the back left and right extrusions here. These are for the rear panel mods we'll use shortly, and I forgot to add them earlier, so I had to do some more backtracking to add them. Then we can switch to the bottom of the printer and add the bottom panel. This is basically just following the Voron 0 instruction manual. Now switching to the sides, we're going to add the side panels. The stock Voron ones are solid pieces of plastic. This is not particularly good since in the back of our printer, the airflow starts at the bottom and has nowhere to escape. So I went over to my CNC and cut out these airflow holes in the panels. So the general idea now is that the airflow will start at the bottom and flow up through the components and out the top left and right. If you don't like this design, there's also plenty of other designs for adding air holes to the rear panel instead. Anyway, aside from the extra holes, these panels just install on the printer using the stock clips on both sides. Next, I'm going to switch to the front of the printer where we can install the front door. For now, this is completely stock. For installing the magnets, the instructions recommend using super glue, though the tolerance in the holes is pretty tight, so I didn't need to use any. You also don't need to measure the distance between the 2 magnet holders, since you can just attach the door handle temporarily and tighten the pieces with the right spacing. And ta-da, we now have a functioning door. The last set of panels go on the back of the printer. I started by trying to add the top panel with these stock adapters. This didn't go to plan since this screw hole didn't seem to line up. There's not a lot of tolerance in the panel gaps, so I'm guessing the tulip motor mounts warped a bit when I was hammering them together. So you know what that means, I'm going back to the CNC to chop off another 1mm off of this panel. And now after all that hacking, it fits. Now for the bottom panel, I'm going to be using this hinged panel mod since I'm still going to be opening this thing up a lot. I'm also going to be adding a custom magnetic latch to the panel, so for that to fit, I'm intentionally making this panel slightly shorter. Also, quick side rant, I bought these ACM panels and was a bit annoyed to find they came slightly warped. This doesn't end up causing any issues, but is annoying when assembling this thing. Anyway, the hinge mod pieces screw in on the right side of the panel. Then for the left side, I 3D printed these magnet holders. The ones that go on the panel have magnets pre-inserted while printing the pieces to avoid needing glue. Then we can just finish screwing everything together and the panel pieces attached with VHD tape. And now we have a nice back panel door to make it easier to mess with the electronics more in the future. The last panels I need to add are for the top hat. There's nothing special about this for now, and I'm just using the instruction manual to assemble this. And it screws into the panel clips we added a bit earlier. Finally, here's what it looks like when you open and close this thing. To keep things simple, I didn't add any of the locking mechanisms for keeping the top hat closed. So it only took like 6 months, but we finally made it to the end of the Voron 0 instruction manual, so I guess I should probably start using this thing. I don't know about other people, but usually when I'm not using my printers, I keep them powered off to not waste extra power while idling, and then flip them on when I want to use them. Though the annoying thing about modern printers is that they're loading entire operating systems at this point, so a lot of new ones take upwards of 20 seconds to power on. For reference, I still have some old Prusa MK3s lying around, and those also print perfectly fine but only take a few seconds to start up with a much weaker microcontroller. As you may recall, I'm using a Raspberry Pi to run all the software for my printer. The actual printer related code is all written in Rust, so it takes less than a second to load, but the Pi is running a Linux-based Raspberry Pi OS image, so that's probably going to take much longer to start up. Just to isolate things a bit, I grabbed another Raspberry Pi and flashed it with the stock Raspberry Pi OS Lite image. If I plug it into a monitor and power, you'll measure somewhere around 30 seconds before you get to the login screen. Just be aware that how you measure this affects things a lot, since just plugging in a monitor will add extra overhead, and you should avoid measuring the first boot after flashing, since the first boot needs to do extra initialization of stuff like SSH keys. To take better measurements, I unplugged my screen and hooked it up to this test board. I made this thing a while ago for my JBOD build video, and this thing has a bunch more functionality than what is needed for this project. For this demo, the important thing to know is that at some point in time, the board will turn on power to the Raspberry Pi and start a timer. Later, I have a one-line program set up on the Pi that will toggle a GPIO pin high when it has finished booting. The test board will notice this and stop the timer. This is all controlled by a command line program that runs on my computer as shown here and displays the resulting measured boot time. Here's the results after I did some measurements with different stock images. Note that if you use one of the newer Pi 5s, it does boot significantly faster, but still takes at least around 20 seconds to boot. I also tried with the Clipper mainsail image, and that is quicker than the stock image, but still fairly slow. If you include the time needed to load a minimal Clipper config, that adds around 6 seconds to the time. In my experience, that's fairly typical since loading Python code takes forever. If you dig into the OS logs for the stock image, you can figure out that the main stages in the boot process are as follows. First, the Raspberry Pi has a bootloader which takes around 10 seconds to load into the stock OS. The bootloader is basically doing the initial hardware initialization and loading the core Linux files into memory. So if you use a smaller Linux image or have a faster boot drive like an SSD, this will go slightly faster. The annoying part is that this part is closed source, so it is hard to tune aside from a few of the flags exposed by the Raspberry Pi team. Anyway, next is the core Linux kernel, which takes around 4 seconds to load and is loading all the drivers for all the hardware you have. And lastly, the user space part is the part that does things like setting up networking and loads all the main applications on the machine. This last part takes around 15 seconds to boot since it has a bunch of applications that aren't really needed for server-style use cases like this one. If you're curious, you can read this doc that's linked in the description if you want to learn about every little command and flag I found so far to make this faster. The TLDR is that I recompiled the Linux kernel with fewer dependencies, disabled the initramfs, switched to a simpler network loading process, and am using a custom config.txt to skip some of the load time in the bootloader. The end result is that we can get down to less than 10 seconds of total boot time after applying power on a modern Raspberry Pi. Note that there are blog posts online from several years ago that are able to get boot times in the order of less than 5 seconds, but those results are all on older Raspberry Pi models that don't have as complicated of a bootloader as the more modern ones. As far as I can tell, my results are the best anyone has gotten on a modern Pi 4 or 5. If you switch to using NVMe drive, you can probably cut these by another half a second, but for now I'm optimizing for fast SD cards since they don't take up more physical space. If you want to reproduce this yourself, I have a custom Raspberry Pi OS image linked in my GitHub, which has all the optimizations pre-applied. Now that we've figured out how to boot the printer, I still need a way to control the printer. As you probably noticed, I didn't install any screen on the front of my printer, so I'm not going to be using that for controlling it. Instead, I have it network connected via Ethernet so that I can directly upload to it from my computer. So a few years ago, I made this Octoprint-inspired web UI that I use to control all my CNCs and other 3D printers in my house. Well, I finally updated it to work with my custom printer firmware, though my firmware doesn't support dumping all the internal state yet, so that's why the UI is still a bit sparse. But this still has all the standard features you'd expect, like a camera preview with recording functionality, a live view of what is going on, support for streaming G-code files to the printer, and some graphs for recording things like temperature metrics. For the camera part, usually I just record the entire live feed like this and later delete it after a week, but ideally I would have support for making sped up time lapses of the entire print. The naive option is obviously to do something like this, where I just increase the video speed by 30x, but there are a few problems with this. First, as you can already see, the toolhead shakes around a lot if you just uniformly speed up the frames. And second, there are a lot of frames that look like this, where the toolhead is in front of the print so you can't actually see what is being printed. Ideally, we'd only pick out frames like this one, which are out of the way of most of the print. I think the gold standard in this area is to use a plugin like Timelapses that'll insert moves into the print so that the toolhead moves completely out of the way before a frame is triggered. Usually these plugins will take one picture for every layer in the model. Personally, I don't like these methods though, since modifying the print will slow it down and reduce the print quality. In my UI, what I've done instead is pre-calculated all the points that are visited in each layer of the print job, and then in each layer, I pick one blue dot here, which is roughly the furthest point from the camera. These points also tend to line up from one layer to another, so in theory the print head shouldn't move much between these points. When my UI sends a print command to the printer's firmware, the printer enqueues the move and returns the exact time at which the move will complete. So the UI will record the nearest frame taken by the camera at the motion completion time to generate a time lapse that looks like this. This is all done in software right now with no modifications to the print, and there are no extra GPIOs required for triggering. There is still a little bit of jitter, which I think is due to a mixture of very fast perimeter moves and the camera not having its shutter perfectly synchronized to our printer's clock yet. Don't be surprised if you see a video from me in the future using an externally triggered global shutter camera for this. Anyway, that's it for today. This was a shorter episode since it took me a while to finish cleaning up all the project documentation for this. Let me know in the comments if there are any opinions on seeing more longer or shorter form content for this build. The next video is probably going to be either input shaper related, or if I'm lazy, I'll just make some more custom electronics. Bye.